Myself, Dr. K. Viswanath Allamraju, Institute of Aeronautical Engineering, Department of Mechanical Engineering, Dundigal, Hyderabad. In this session, we are going to study section modulus and also some of the problems, how the section modulus is being applied in problems. Coming out to the course outcome and Bloom's taxonomy, it is related to this topic is related to the course outcome of number 4 and apply the knowledge of theories of failure, shear force and bending moment relations for analyzing the flexural shear stress distributions and failure of beam sections. This is the course outcome number 4, and the Bloom's taxonomy level for this topic is apply. What is section modulus and what is the significance of section modulus? From section modulus can be derived from the simple theory of simple bending equation. The bending equation is m by I equal to sigma by y equal to E by R. This is a simple bending equation where m is bending moment. The unit for m is Newton millimeter or Newton meters, and I is the second moment of area or area moment of inertia. The unit for area moment of inertia is mm per 4, where sigma is the stress, normal stress or bending stress. The unit for the bending stress is Newton per mm square millimeter, and y is the distance of a fiber from neutral axis. The unit for this y is millimeters, and E is the modulus of elasticity. Unit for modulus of elasticity is Newton per square millimeter, and R is the radius of curvature. It is in millimeters. So this equation is known as pure bending equation. I is the area moment or second moment of area varies based on the cross section of the beam, where m is the maximum or bending moment. This bending moment can be derived. This can be calculated from the concepts of shear force and bending moment equation. Now here, from pure bending equation, this m by I and sigma y, where m equal to sigma maximum times I by y max. Here the stress sigma becomes maximum when y is maximum. Hence, the above equation we are going to write m by I equal to sigma maximum by y maximum, and m equal to sigma maximum times I by y maximum. Now we know that I by y maximum is known as the section modulus. Section modulus is the ratio of moment of inertia to the maximum distance of the neutral axis to the fiber. This z equal to I by y maximum. Now substitute in the place of I by y max, substitute z in the place of I by y maximum. Then the equation of bending moment, that m equal to sigma maximum times z. Now here this z is z maximum or maximum section modulus, and whereas m becomes maximum bending moment. M becomes the maximum bending moment. Now here very important is that the significance of section modulus represents the strength of a beam or strength of the section. How the strength of the section it represents. Now here in this equation, m equal to sigma maximum times z. Here m is the maximum bending moment, Maximum bending moment means the moment of resistance of the section offered by the section is maximum. That is, the moment of resistance is high. This moment of resistance becomes maximum when Z becomes maximum. Z represents a section modulus. The section modulus becomes maximum. That means when moment of resistance is high, that means when strength is high, the moment of resistance becomes high. That means here which one that section represents. The section modulus represents, if the section modulus is high, then the moment of resistance to bend becomes high. So here the section modulus represents the strength of a section. Section modulus represents the strength of a section. That's why M equal to here sigma maximum times Z. This equation is very important for calculating the moment resistance. And also this equation is so important to find out geometry of the beam or length of the beam or width of the beam or breadth of the cross section of the beam. And also from this equation we can find the uniformly distributed load over the beam, whether the beam can be a simply supported beam or cantilever beam or fixed beam or overhanging beam. So the what type of load, and one more thing also, from this equation we can find out the failure stress or maximum stress of a beam, where the beam can carry the maximum load. After that, the beam failure takes place. Failure of the beam can be observed. That stress can be calculated by using this equation. That is M equal to sigma maximum times section modulus. Sigma maximum times Z. This Z is equal to I by Y max. So this Z is important. The formula mathematical equation is so important. And also Z varies from section to section. Suppose if the Z is some formula for rectangular section, and it will changes for square section. For I section it is different. Let us observe the various section modulus of various beam sections. Now here it is the rectangular section. For rectangular section, let us glance here where moment of inertia about neutral axis, that is I equal to BDQ by 12, where B is the width of the beam, D is the depth of the beam. So I equal to BDQ by 12, Y equal to D by 2, substitute in the equation of Z equal to I by Y max, then we can see that it becomes BD square by 6. So Z equal to BD square by 6 for the rectangular section. And we can derive from this for square cross section also. For the square cross section, B equal to D becomes width, breadth equal to depth. Then Z becomes Z equal to D into D square by 6, or D cube by 6, or B cube by 6. This is the value for section modulus of a square beam. It is for a square cross section. For a square section, section modulus is D cube by 6 or B cube by 6. Suppose for a hollow rectangular section, what is the section modulus? So we have to know the I value for a hollow section. So for a hollow section, the area moment of inertia I equal to B into D cube by 12 minus small b d cube by 12. Now to make it common, the capital B indicates the width, outer width of the beam, outer width, larger width, and capital D outer depth, and small b inner width, and small d inner depth of the beam. it is bd cube by 12 minus small bd cube by 12. That why we have to subtract it, because it is a hollow section. For this hollow section we have to subtract whenever we have to, then the original section will come out. The original, that means for this square, this is the hatched section, can be calculated the moment of inertia, that is area moment of inertia, that is bd cube by 12 minus small bd cube by 12. So 1 by 12 times bd cube minus small bd cube. So what about y maximum? Y maximum, what is the y? Represents distance from neutral axis to the maximum outer fiber. So outer section, the top modes, that's why y equal to capital D by 2. It is not a small d by 2. Small d by 2 means it becomes this distance, inner section, small d by 2. We want y maximum means maximum distance from neutral axis to outside, that is capital D by 2. So y equal to capital D by 2, substitute here both I and y max, substitute in the formula of z equal to I by y maximum. What is that I equal to? That is 1 by 12 times bd cube minus small bd cube by y maximum, capital D by 2. After simplification, these two will be cancelled 6 times. The equation becomes bd cube minus small bd cube by 6 times d. So this is the section modulus for hollow section, rectangular section. If you want to find out the section modulus of a hollow square section, then for a hollow square section, then substitute b equal to d in the formula of hollow rectangular section modulus formula. That is for hollow square section. Hollow square for a hollow square section. For a hollow square section, b equal to d, then it becomes z equal to, substitute b equal to d, then that is d cube, capital D cube minus small d cube by 6d. And one more thing, yes, I substituted here capital B equal to capital D and small b equal to small d. Then what will happen here, bd cube, capital bd cube, then becomes capital D power 4 minus small d power 4, because b equal to d into d cube, that is d power 4, minus b equal to d, that is d power 4 by 6 times d, the section modulus of a formula. Z equal to capital D power 4 minus small d power 4 by 6 times d. So this is the section modula for hollow square section. This is the formula, section modulus for hollow rectangular section. For square section, width equal to depth with the same geometry. All sides are equal for square. Whereas for a rectangular section, two sides are equal, that is b, and one more side is the d. Now another section is the circular section. Consider the circular section here. If we consider the circular section, it is having a diameter d. The diameter is d. Then the formula for the second moment of inertia of a circular section, I equal to pi d power 4 by 64. Pi d power 4 by 64. And what about y maximum? From neutral axis, the topmost layer, that is y maximum, that is capital D by small d by 2. So y maximum equal to small d by 2. Substitute both I and y in the formula in the section modulus z equal to I by y maximum, that is pi d power 4 by 64 by d by 2. Then it becomes pi by 32 times d cube. Z equal to pi by 32 times d cube. The unit for section modulus section modulus is millimeter, cubic millimeter. So this is the section modulus formula for hollow circular section. And if we consider the hollow circular, the section modulus of a solid circular section. For hollow circular section, pi into capital D power 4 minus small d power 4 by 64, that is the I value. Area moment of inertia, that is the capital I, pi by 64 times capital D power 4 minus small d power 4. And what about y maximum, that equal to capital D by 2. Substitute in this I and y maximum, z equal to I by y max. What is that? I, pi by 64 times capital D power 4 minus small d power 4, and y maximum equal to capital D by 2. After substitution, the observed relation, observed formula for section modulus, here it is, z equal to pi by 32 d times capital D power 4 minus small d power 4. Here capital D is outer diameter. Small d is inner diameter. Okay, and the unit for the section modulus, again, the unit for section modulus is millimeter cube. So here for a hollow section, or if you substitute for solid circular section, if you want, in the hollow circular section, if you substitute small d equal to 0, then we can see, understand, it becomes pi by 32, pi d cube by 32. For solid circular section, if you want section modulus, take the formula for hollow circular section. In that hollow circular section, if you substitute inner diameter equal to 0, then what will happen? It becomes, the formula of section modulus becomes pi d cube by 32. Here where d is the diameter of a circular section. That's what we observed here, pi d cube. That is okay, pi d cube by 32. So the unit for section modulus, again repeating, millimeter cube. So these are the various sections we have studied, section modulus of various sections. Now let us solve some of the problems by using these formulas, whatever formula we have learned or we have proved. Mainly the maximum formulas are used here. M equal to sigma maximum minus z, where z equal to I by y max. So by using these two formulae, we can derive, or we can find out the unknown parameters by using these two formulae. Now, what is the M for simply supported beam? M equal to M is different from cantilever beam. And when the beam is subjected to point load, the maximum bending moment is different from when the beam is subjected to uniformly distributed load throughout the length. But the relation we require here, the maximum bending moment, where will it occur? That formula we have to know it. So this maximum bending moment concepts already we have studied in the sections of shear force and bending moment diagrams module. There we can know it, how to calculate the maximum bending moment relations with the different sections and different loads at different supports of the beam. Now here it is, the formula is a cantilever of now the problem is here, a cantilever of length, a cantilever beam of length 2 meters fails when a load of 2 kilonewtons is applied at the free end. So if the section of the beam is 40 millimeters by 60 millimeters, that means it is a rectangular section. Find the stress at the failure. What is the failure stress? That is nothing but the maximum stress it can, after which failure takes place. Now let us, the given data, let us write down the given data. Here it is. Length of the beam L equal to 2 meters, that is 2 into 10 cube, that is 2000 millimeters. And width of the beam is 2 kilonewtons, that is 2000 newtons. Now the section of the beam is rectangular section, that is we have to consider which one value is the breadth and which value is the depth. For rectangular section, the depth we consider is the maximum value is the depth and the smaller value is the width, that is b equal to 40 millimeter and d equal to 60 millimeters. So for this, what is z equal to I by y max? What is the I value? I value for the section, that is BD cube by 12, y maximum that equal to d by 2. Substitute both, then z equal to BD square by 6. B value, that is 40 millimeters, D equal to 60 millimeters, substitute over here, then Z can be known. Then we have to know it, what is the maximum bending moment for a cantilever beam is subjected to a point load at the free end. So consider the free load is W and length of point load is W and length of the beam is L, then it comes, that is WL is the maximum load, that M equal to W times L. After knowing this maximum bending moment and Z value, after substituting in this formula, that is M equal to sigma maximum times Z, then the sigma maximum, the maximum stress can be calculated. And let us begin. Now here the section modulus of a rectangular section is, we know the equation, that is Z equal to BD square by 6. Here Z equal to BD square by 6, substitute B and D values in this formula and we can observe the section modulus value. Here it is 24,000 cubic millimeters and the maximum bending moment for a cantilever beam is at the fixed end. So here M equal to W times L, M equal to W times L, where W is the point load, that is 2000, that is 2 kilonewtons. Convert into newtons, it becomes 2000 newtons. L is 2 meters, convert into millimeters, it is 2000 millimeters. So 2000 into 2000, that is 4 into 10 power 6 Newton millimeters. Here the W value in newtons and the length value is in millimeters. That's where the unit for bending moment is in Newton millimeters. That is 4 into 10 power 6 Newton millimeters. Now here we consider the maximum stress is the stress at the failure. That is the maximum stress. Here the stress strain diagram, their maximum stress is different from failure stress. The maximum stress in the case of stress strain diagram represents the strength of a material. This is the failure stress, sigma F. This is the maximum stress, that is called ultimate tensile stress, is the maximum stress. In the case of a stress strain diagram, for stress strain diagram, maximum and failure, but here it is the maximum stress is the sigma maximum stress, that is the stress at the failure. So we know the relation, that is maximum M equal to sigma maximum times Z. We know the Z value and you can substitute sigma maximum M equal to sigma maximum times Z. Then sigma maximum equal to M over Z section modulus. Here what is the M value? 4 into 10 power 6 and Z value is 24,000 millimeters. Then after substitution, the maximum stress is calculated as 166.67 Newton per square millimeters. How it is here, M is in Newton millimeters, Z is in millimeter cube. So Newton millimeter by millimeter cube then becomes Newton per square millimeter. So the observed stress, the stress at the failure is 166.67 Newton per square millimeter. For a cantilever beam is subject to 2000 newtons at the free end, and the length of the beam is 2 meters. So in order to avoid the failure of the cantilever beam, how much load should be applied? It should be the stress should be less than 166.67. It should be less. That means less than 2 kilonewtons should be applied. Otherwise, failure takes place. Already mentioned here, the failure takes place to 2 kilonewtons. So the stress developed is this much. So this much stress failure takes place. That's what we studied. And coming to next problem, here a rectangular beam 200 millimeters deep and 300 millimeters wide is simply supported over a span of 8 meters. What uniformly distributed load per meter the beam may carry if bending stress is not to exceed 120 Newton per square millimeter. This bending stress is the sigma maximum, is the maximum stress. So what to be found here? What is the objective and what is the data was given here? The data was given here. It is the section, the dimensions of the section of the beam, that is 200 millimeters deep and 300 millimeters wide. But the type of beam here, it is simply supported. But what is the length, the span of the beam? Here it is 8 meters. 8 meters. And also one more thing. The maximum stress is given data. Here it is 120 Newton per square millimeters. But what to be found? What is the uniformly distributed load W per meter length? Such a way that 120 Newton per square millimeter can be obtained for the section of 200 millimeters deep and 300 millimeters wide. Here the maximum value is width of the beam. That's why it's the section of the beam. The section of the beam. So what is the value of for this? It is comes under the section of the rectangular section. For a rectangular section modulus is bd square by 6. Substitute b value and d value in the formula which was given here. The b breadth is 300 millimeters and the depth is 200 millimeters. So after substituting the breadth and depth, then we can find out the value of the section modulus, that is bd square by 6. That is 300 into 200 square by 6. That is, here it is the value 2 into 10 power 6 cubic millimeter. That is section modulus. But here, given here, one more thing, sigma maximum stress, that is 120 Newton per square millimeter. So there are two figures. This is the beam carrying uniformly distributed load, and this is the section of the beam. The section of the beam is rectangular, that is 200 millimeters deep and 300 millimeters wide or width. Here the type of beam, here it is simply supported beam. So what is required here? For a simply supported beam, we have to know the bending moment or maximum bending moment. What is the moment resistance? Okay, that for this case, and where it will occur, it occurs at the midpoint. So how to find out the formula? By using that formula, you will substitute in that equation maximum bending moment. After getting in the maximum bending moment, after substitution, then we know the sigma m equal to sigma maximum times z. We know the sigma maximum, we know the z. From this, in this m comes in terms of the value small w. That is the small w is the uniformly distributed load. Thus, we can calculate uniformly distributed load. Okay, in that manner we can complete. Thank you.
Like, share and subscribe. hit the bell icon for more updates.